Okay, so here's where we're at. So this is kind of like the third step in these three units. So the first one was velocity. Okay, how do you measure where things are? How do you measure the rate of change? How do you do vectors? That type of thing. Last unit we just got done with was acceleration. Okay, well that's the rate of change in the velocity. Okay, that's cool. And how do we use that? How do we use the equations? That type of thing. And so the third unit of this trifecta is going to be forces. Okay, so this is kind of like the capstone, the culminating thing of everything that we've studied so far. And so this is going to take, this is one of the longest units that we have. This unit takes us about 2.5 weeks to get through. Okay, but the dichotomy about forces is that it's one of the biggest units, but there's not that many equations. You just have to figure out how to use the same equation in different ideas. So when you look at this idea of forces, and today is a good news, bad news day, okay? So the bad news is I've got to lecture and do demos and things like that. The good news is you don't have any homework tonight, so not a bad trade. So when you look at what forces are, okay, and the short version of a force is that, and this hinges all on one word, okay? A force is something that is capable of causing an acceleration, okay? Not necessarily is going to do that, but it's capable of causing an acceleration. So let me give you a simple example. So here's Hector sitting back here in his chair. Okay, I apologize for put glasses on. Okay, there's Hector. Now he has glasses. Now we know it's Hector. Okay, and so Hector's sitting there, and gravity is pulling down on him. Okay, and you all are aware of this idea of gravity. Okay, you've been aware of gravity since you were a toddler. Okay, and maybe you knocked something off the table, or you fell down, or you were bouncing on the bed and you bounced off. Okay. Gravity is one of the first fundamental forces that you have encountered, okay? And gravity is a wonderful thing. We'll spend a lot of time talking about gravity. Because without gravity, we wouldn't be here having this talk, okay? So one of the cool things about our universe is that there is gravity, okay? Because without gravity, stars would have never formed. We would never be here because we would have never combined the lighter elements into the carbon, nitrogen, oxygen, iron, magnesium, everything that makes you up. So without gravity, you would never have stars. Without stars, you wouldn't have us. Okay? So gravity is kind of an important thing. So gravity is pulling down on Hector. Okay? And later on, you'll see that there's a couple of different ways you can calculate the value of that gravitational force. So one option is that you can use this equation, Fg equals mg. So when we begin to talk about forces, a lot of times we're going to use subscripts to indicate what that force is, okay? So for example, if we're talking about gravity, we're going to call that F sub g. If we're talking about friction, okay, so like if I take this and I push it, that ball of twine, it's going to come to a stop because there's friction. Y'all, if you drove your car today to school, you took advantage of friction. Because without friction, number one, your car would have never moved, and without friction, your car would have never stopped or been able to turn. You wouldn't have been able to like grab your shoelaces and tie them because you wouldn't have been able to hold on to your shoelaces. So it's like, okay, that's kind of awkward. Did you tie your shoes? Nope, couldn't hold them. Okay, the string just slipped out all the time. So friction's a good thing. So if we're talking about friction, we're going to put that as like F sub F. Okay, a lot of times we'll talk about applied forces. Okay, that might come from an engine, a push, a pull, something like that. So we're going to be dealing with all these different types of forces. And so if you look at Hector sitting here, if we know Hector's mass, let's say that that's, I'm just going to make up a number, 50 kilograms. And if I multiply that by the acceleration due to gravity, which you all know to be 9.8 meters per second squared, this is why we studied acceleration first, and I multiply those two numbers together, I get 490 newtons. So right now, this strange rock that we're on, we're orbiting a very ordinary star that we call our sun. this rock that we're on is creating a gravitational field. And so Hector is being attracted to the Earth, okay? And we'll talk about Newton's laws of motion, and those are on the back side of the lecture notes I gave you. Newton's third law of motion says that for every action there is a reaction. So the Earth is pulling down on Hector, but Hector is pulling back up on the Earth with an equal and opposite force of 490 newtons, because every force is said to be coupled. So Hector's sitting there, and gravity is pulling down on him. Okay, so this is a classic example of a force acting on Hector, but he's not accelerating. Okay, so gravity is pulling down on him. Now, here's how I can check that that force exists. I won't do this because I like Hector. Okay, this would be rude. I don't do this. But I could walk up behind Hector and I could grab a hold of his chair and I could pull that chair out from underneath him. Okay, well, I won't do this. Okay, but now if I did that, what would happen? Hector, what would happen to you? What would you do? You'd begin to accelerate, right? Because then there's an unbalanced force. So right now, the chair is pushing up on Hector with what we call F sub n, which stands for force normal. We'll spend a lot of time talking about normal forces. So right now, these forces are balanced out. If you want to make this a negative value, because that's acting downward, okay, hey, there's a downward force of negative 490 newtons. There's an upward force created by the chair of positive 490 newtons. Okay, it's cool, right? And right now, everything adds up to equal to 0. Now, here's the other beauty of every force problem I'm going to give you. Okay? Every force problem can only end up in one of two ways. Either all the forces add up to equal to 0, like in Hector's case, as he sits there, and they add up to equal to 0, and you're at the constant velocity. Okay? Now, that doesn't necessarily mean that you're at rest. It just means you're moving at a constant velocity. So if I take my cup and I push it along and it moves at a constant velocity, all the forces add up to equal to 0. Now, the other option is that things accelerate. So if I take Hector's chair and I pull it out from underneath him, oh, the forces don't add up to equal to 0, and Hector accelerates. So literally, every force problem I'm going to give you can only do one of two things, and there's only two things that I can make it do. I can either have it at a constant velocity, and all the forces add up to equal to 0, or you accelerate and the forces don't add up to equal to 0. Literally, those are the only two things that I can do on every force problem. That's it. So when I type up a problem, that's the decision that I have to make. Do I want to have Hector move at a constant velocity and all the forces add up to equal to 0? Or do I want to make Hector accelerate and the forces don't add up to equal to 0? That's it. Those are the only two things that I can do. That's it. I can't, well, maybe I'm going to make Hector kind of accelerate. Okay, no. Hector is either accelerating and forces don't add up to equal to 0, or he's at a constant velocity. That's it. Now, once I make Hector accelerate, then I have another two choices. Do I want to make Hector speed up? Do I want to make Hector slow down? So once I make that decision to say, I want to make Hector accelerate, then I decide, is he going to speed up or is he going to slow down? That's it. So basically, every force problem can only end up in one of three ways. You're at a constant velocity, or you're going to accelerate, and then within that, you're either going to speed up or slow down. That's it. Every force problem that you are going to have can only be one of those three things. Speed up, slow down, constant velocity, the forces add up to equal to 0, or they don't. That's it. There's nothing in between. That's it. So when you keep that in mind, okay, everybody says, forces are complicated. No, they're not. Those are the only options that I have, okay? Only question is, what am I going to make, what's the force that's going to make Hector speed up? Am I going to let gravity do it? Am I going to strap a rocket engine on Hector and make him accelerate that way? Am I going to, shoot him up in the air, hooked up to a hot air balloon? Okay, I don't care. But here's the point: if Hector is going to accelerate, the only way he's going to accelerate is if there's an unbalanced force. That's it. Okay. It's just what's going to be the source, and it's got a little bit poetic, is what's going to be the source of the force. Now, let's talk about gravity. So, on the lecture notes that I gave you, okay, one of the big equations dealing with gravity, and this falls under this concept of the four fundamental forces. So if you look at like the history of science, we've had some mistakes along the way. The whole idea of like, are we an Earth-centered solar system, or are we, a sun-centered solar system? We've screwed some things up along the way. But if you look at where science was at the end of the 1800s, early 1900s, about 100 years ago, okay? Science was actually kind of a depressed state, because at that time, science thought they had everything figured out. So the main thing that they had figured out at that point is gravity. So if you look at the fundamental forces, there's four of them, but in the early 1920s, about 100 years ago, there was only two of them. One of those is gravity, and we're going to spend a lot of time talking about this. Do not worry about this for now. We're going to use this equation a lot later on. I'm just painting the picture, okay? And that's big G, and big G is what's known as the universal gravitational constant, okay? It's just a number. Just accept it for now. It's just a number. Don't worry about it. We'll deal with it later. And then it's M1, M2, and then distance squared. Okay, so what that means is that every object that has mass is attracted to every other object in the universe that has mass. So right now you are obviously attracted to this big rock that we're on. Okay, so I could take Hector's mass, and I could put in the mass of the Earth, and I could put in how far Hector is from the center of the Earth, and I could calculate the gravitational force that exists between Hector and the Earth. If you happen to notice, there was like a quarter moon in the sky this morning, okay? Anybody see the moon? It's kind of cool, okay? It's a quarter moon visible right now, so Hector is attracted to the moon, okay? So if I knew the mass of Hector, the mass of the moon, and how far apart they are, I could calculate the gravitational attraction between Hector and the moon. I could calculate the gravitational attraction between Hector and the sun, between Hector and Jupiter. I could calculate the gravitational attraction between Hector and the most distant electron in the most distant galaxy, you name it. So the only way that you could be in zero gravity, and this is like the ultimate freshman mentality, the only way that you could be in zero gravity is literally if you were the only thing that existed in the universe. Okay, that's the only way you could be in zero gravity. As long as there is anything else in the universe that has mass, you are going to be gravitationally attracted to it. Now, let's talk about the bottom number. Because you're dividing by distance squared, this is what's known as an inverse square law. So what that means is if you increase the distance, the force becomes smaller and smaller and smaller. So one way I'm going to show that is that you can model it with a magnetic field. So this is a substance in here called ferrofluid. It's very finely suspended iron particles in a dark oil. And this is just your basic magnet. And so if you bring this magnet up to it, you'll see that it kind of does some weird things. You get these pointy-like structures, okay? And if you pull this back, you'll notice that the particles will fall, okay? So what this is a classic example of something known as an inverse square law. You can do it like this too on the bottom. You can drag this stuff around, okay? It's kind of cool. So I'm going to pass this around. The only thing I want you to see on, beyond the fact that it's just cool, is the fact that gravity exists not as a continuous field. Gravity exists in what we call field lines, and that's why you get these pointy little projectiles that come out from the surface of that. The other thing why I'm going to pass this around is this is what's known as an inverse square law. So this is a visual way of showing that. So when the magnet is really, really close, you get this really, really, really intense magnetic field. okay? And you can tell that because of the fact that the structures are very, 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 very tightly packed. So as you move this away, what you'll see is that they become more and more spread out because you're getting further away from the magnet, and as you get further away from the magnet, the strength of that magnetic field becomes weaker and the lines aren't as intense, okay? So I'll just pass this around, it's just fun to play with. If you're looking for something, if you really think this is cool, you can go to Amazon and buy ferrofluid and magnet. So yep. Hours of entertainment fun. Okay. Miracles of modern science. So when you look at, thank you. Hold on. So the gravity has been called the great architect of our universe. Because if you go back about 14.6 billion years, give or take about 10 minutes, there was an event called the Big Bang, which is oddly enough a misnomer because there wasn't, everybody has this idea of the Big Bang like it was an explosion, okay? Like you could have been outside watching it like a fireworks go off. Okay, like like an exploding mortar or something like that. Like people could have been outside watching this event. And this is what happened. Big Bang is what's known as singularity. We don't know what happened prior to that. All we know is that all of the universe, all the energy, all of the mass, everything was contained in what we call a singularity, an infinitely dense point. And we don't know what happened, but something happened. Something tipped the scales. And that infinitely dense material began to expand. And so when it expanded, the universe itself began to expand. And out of that, you created space and time. So as the universe expanded, space and time was actually being created. So you can somewhat visualize it like you drop a rock into a pool of water, and that leading wave expands. So that's kind of like what the universe did. But it expanded like in a three-dimensional situation. So imagine like a balloon pops and you're expanding in all this direction. So one of the cool things that happened out of all this is that literally the universe had to cool down for a while. And there's a whole study called cosmology that just basically deals with the Big Bang, and you get into this idea of hyperinflation and the universe was expanding. And we have a pretty good idea of what happened. And so one of the things that happened is that the universe began to cool down. And as the universe cooled down, energy changed from being energy into mass. And then you began to get electrons, and you began to get protons, and you began to get neutrons. And so those existed within this area that was being spread out. And for whatever reason, there were regions that had slightly more dense areas. If the universe, when it expanded, had been completely uniform, and it expanded in equal directions in all areas, we wouldn't be here having this discussion. So, because without anomalies within that where you had a slightly bigger gravitational field, we wouldn't be here having this discussion because the universe would have never started to form stars. So what happened is that, for whatever reason, there was difference in this density. And particles began to stick together. And so what happens is that it becomes almost like a self-fulfilling prophecy, in the sense that, as the mass began to stick together, that created a stronger gravitational field. As that created a bigger gravitational field, then that attracted even more mass together. And as that mass got bigger, it created a stronger gravitation. So it kind of snowballed, okay? And so eventually what happened is, if you could have seen the universe at that time, there would have been like this kind of like eerie glow to it, okay? Because this energy was all spread out. And then after a while, and I say a while, it isn't like it's 5 minutes, okay? After about 100 million years, we think the first stars began to form. And so it would have been cool if you could have seen this. All of a sudden, you would have seen lights started to show up. So if you've ever been like outside at night during the summertime, you see like fireflies, okay? You see fireflies that begin to like pop up and glow. That's what you would see in the universe. As these stars began to form, triggered by gravity, and the hydrogen got pulled in, and the pressure increased, and the temperature increased, the gravitational field got stronger and stronger and stronger. Eventually you started this fusion process where hydrogen bonds together to make helium. And out of that you get a release of energy. And so what you would see is that you would begin to see these points of light appear in the universe as these first generations of stars begin to form. Now we wouldn't be here having this discussion at that point because the only elements that existed basically were hydrogen and helium, a little bit of lithium, but nothing. The periodic table quiz that you take in chemistry would have been really easy. It would have been a 2-question quiz. Hydrogen, helium. Okay, that's it. You're either going to get a 0, a 50%, or 100%. That's it. Okay? So out of that, then those first generations of stars actually exploded. So then you destroyed the factory that was producing the stars. And out of that collapse, then that's when you began to form the more massive elements that make us up, like carbon and nitrogen and oxygen. So if those first generations of stars hadn't exploded, we wouldn't be here because you wouldn't have ever made the heavier elements. So those elements got kicked out, and then you started the second generations of stars and third generations of stars. So there's an old cliche in cosmology and astronomy that says we are all made of stardust, okay? And it's true, literally. Like every heavy element that makes you up at one point was in a star. And that star collapsed, and it got kicked out, and then this, called an accretion disk, which is a fancy word for a spinning pile of junk, okay, atoms and things, that began to coalesce again, and that coalesced into this strange rock that we're on, and we happen to have a really stable sun, and it's been burning for about 5 billion years, and it's burning for about another 5 billion years, give or take about 10 minutes or so. And so that's a cool thing, and that allows us to exist, and we have an atmosphere. So there's a whole bunch of things that had to happen just right for us to be here, even if you look at us having an atmosphere. So if you consider an apple like this, okay, like let's say, for example, you cut an apple in half, and this is the size of the Earth. What allows us to exist is an atmosphere that's about as thick as the peel on an apple, on a relative size of the Earth. Our atmosphere is that thin red layer. And without that, we won't be here, okay? Space is a horrible thing. Everybody says, oh, let's go to Mars, let's travel interstellar, okay? Space is basically just there to kill you, okay? You have radiation, you have micrometeoroids, okay? You have gamma rays, all these extremely high energy particles, okay? Space is not a pleasant thing. Everybody says, oh, let's go to space. No, okay? Space will kill you given the chance, okay? It's a vacuum. You get this straight radiation from the sun, nothing to filter it out, okay? Space is horrible. Let's go to Mars. No. It's horrible, okay? Sounds good, but in reality, it's just not. So we have enough atmosphere. We have an atmosphere because we have a strong enough gravitational field. The moon does not have an atmosphere. Okay, if you go out and look at the moon, you'll never see clouds on the moon. You want a boring job? Be the weatherman on the moon. Okay, the boringest job in the world. It's either sunny and hot or it's dark and cold. That's it. Okay, what's today's forecast? Sunny and warm. What's the high temperature? The same as it has been for the past 1,000 years. What's the forecast for tomorrow? The same as it's been the last 1,000 years. Okay? Mars doesn't have an atmosphere. Doesn't have a strong enough gravitational field. Mars also doesn't have a magnetic field. Okay? Because it doesn't have a magnetic field, even if we could get an atmosphere back on Mars, it is, oh, let's create an atmosphere on Mars. It's a train wreck. Can't do it. Okay? You can make it, but it's not going to hold it. Because Mars does not have an active magnetic field. So a compass, if you get to take things with you to Mars, don't take a compass, it won't do any good, okay? Because it doesn't have a magnetic field like the Earth does. So because the Earth has this magnetic field, it takes all these highly charged particles that are being bombarded, that are bombarding us all the time, and it interacts with that magnetic field, and it forces those charged particles to the north and south pole. So if you ever heard of like the northern lights, okay, or the southern lights if you're in the southern hemisphere, okay, those exist because our magnetic field is taking all of those very, very highly charged particles that would normally bombard us and screw up our DNA, which is a train wreck, and it directs them to the poles, okay? It also allows us to keep an atmosphere because our atmosphere is made up of all these nitrogen and oxygen molecules, okay, bouncing around. That's kind of cool. And we have this atmosphere because of the fact that it's like two competing forces. We have a magnetic field that deflects those charged particles so that way we're not bombarded with these highly charged particles that come from our sun. But we also have a gravitational field that's holding it. Okay, so those two things work together that allows us to have an atmosphere. A magnetic field that keeps these highly charged particles away, and a magnetic field that holds them. This is why Mars doesn't have an atmosphere, why the moon doesn't have an atmosphere. Everybody says, oh, let's go to Mars. No, stop. It's a horrible place to go. It sounds good, but it's really just not viable. So here's what I want you to see out of gravitational field. Number one, it's always attractive. You don't have to wake up in the morning and go, wow, maybe gravity is repulsive this morning. You go to get out of bed and gravity pushes you up towards the ceiling, okay? It's not going to happen. Gravity is only attractive. It's dependent upon the strength of the two masses, okay? Obviously, if you have more mass, you have a stronger gravitational field, okay? And it's inversely proportional to distance. And that's what I showed you with the magnet, okay, and the ferrofluid. Gravity works the same way. When you're really close to that magnetic field, to that gravitational field, you get a really, really strong force. As you increase the distance, as you pull it further away, the force becomes weaker and weaker and weaker. Okay? That's it. So Isaac Newton actually came up with this equation. He didn't come up with the numeric value of G. That was done by the name of a guy by the name of Henry Cavendish. We'll talk more about that number later. So here's all I want you to see. Gravity is one of the four fundamental forces. It's hugely important. You can never be in zero gravity. As the distance increases, the force becomes less. Okay, that's all you need to know out of that. Now, the second one is what we call the electromagnetic force. And that's F equals K, Q1, Q2 over D squared. Now, if you compare that to the gravitational force, which is big G M1, M2 over D squared, notice that these are very similar, okay? In the sense that this K is just a constant. Don't worry about it. It's just a number, okay? It's just a number. These are charges, Q1 and Q2, okay? That's the charge on the particles. Charges are measured in coulombs, okay? And we'll talk more about that later. Okay, it's just a coulomb, okay? Don't worry about it. And then you're dividing it by D squared. Coulombs are a fundamental unit of the universe, just like mass is measured in kilograms, because that mass is a fundamental thing, okay? Charge is a fundamental thing measured in coulombs. So right now, you have billions upon billions upon billions of little subatomic particles that make you up. And they're electrons and protons. And every electron and proton that make up your body, and again, don't worry about this number, I'm just writing it down. Is 1.6 times 10 to the negative 19th coulomb. So every electron, proton that makes you up either has that amount of negative charge or that amount of positive charge. It's not very much. Okay? It's a relatively small number. But the universe that you're used to dealing with on a macroscopic level, oh, gravity, tables, penguins, Oreos, whatever, okay? It's kind of this cool thing. It makes sense. You're used to it. The atomic world gets really fast. So to give you some perspective about what happens on an atomic level, so this is just your basic piece of aluminum foil, okay? And this is one of the things that my Chem 1 students do, is that they calculate the number of aluminum atoms that make up, like if you could see the edge of that aluminum foil, and you could count the number of aluminum atoms that are stacked just on this thickness, okay? From this edge to there, okay? Just the number of aluminum atoms that are stacked up edge to edge to edge to edge. That's about 94,000, okay? Ballpark. It's about 94,000. So just on the thickness of this aluminum foil, this is just one column, okay? It would take about 94,000 atoms stacked edge to edge to edge to edge to edge to get to the thickness of that aluminum foil, okay? So what does that tell you about the size of an atom? Really, really big or really, really small? Really, 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 really small, okay? So atoms are incredibly small. And you all have been through Chem 1, I'm guessing, or most of you. And you learned about, or at some point, you've learned about electrons, protons, and neutrons. Okay, cool. So if you look at the nucleus, and you have your protons and your neutrons, and then around here you have these electrons. That's a whole other story, which we'll talk about in just a second. And we call this the nucleus, and here's the weird thing about those 94,000 atoms. This aluminum foil is about 99% empty space, okay? And you look at it and go, whatever, we're can't. Look at it, it's solid. If it was empty space, like, if I hold this up, it isn't like you all can see me through the aluminum foil, right? Can't see me. What do you mean it's empty space? It is, okay? The atomic world makes no sense, literally. The more you study what happens on an atomic level, the weirder it gets. So if you look at this equation, this is one of the first equations they had. This is one of the fundamental laws. They said, okay, F equals K, Q1, Q2. So if you know you have an electron that makes up a strand of your DNA, and you know that there's another electron either in your finger or on the other side, on the other hand, whatever, you can calculate the force between those charged particles, okay? You can. All you have to have are the two charges and how far apart they are. So if you look at these two equations, they look very similar. It's a constant times two fundamental particles, whether that's charge or mass, and they're both divided by d squared. So if you looked at a chemistry or physics book from 100 years ago, and if you were to look in the index, number one, you would not find the words electrons, protons, or neutrons. We didn't know they existed. Okay, literally, we did not know they existed 100 years ago. We knew that there were charges, okay, and we knew that it had something to do with distance. So here's a simple way to show that. Emlyn, can you give this a spin? So what I have here is your basic balloon, okay? And if I put my hand up beside it, okay, there's a gravitational attraction that exists between my hand and the balloon. My hand has mass, the balloon has mass, okay? Now, it isn't like I do this and all of a sudden the balloon begins to drift towards my hand. Gravitational force, important as it is actually the weakest of the four fundamental forces. Okay, and that's okay, because if gravity had been a lot stronger, we wouldn't be here having this discussion, because the universe would have expanded and then it would go, whoop, and it would collapse back on itself. Okay, it would have been like Big Bang, whoop, big crunch, bad things would have happened. We would never be here. If the gravitational force had been weaker, we wouldn't be here either, because then you would have never started the fusion process, you would have never had stars, and we wouldn't be here either. So there's this balancing act. So gravity is like the Goldilocks force. Not too strong, not too weak, it's just right. So if I put my hand here, my hand has mass, the balloon has mass. If I know the mass of my hand, if I know the mass of the balloon, if I know how far apart they are, I calculate the gravitational force. Now, I'm going to take this balloon, and I'm going to give it a rub with this blanket. Okay? Okay? Now when I do that same thing, now when I put my hand anywhere near that balloon, it becomes very attracted to it. Okay? And all I did was rub it with a balloon. So something had to change, right? Now there's an imbalance between this charge. Because clearly, my hand is very attracted to that balloon. Okay? If I put it anywhere close to that. And again, this is also an example of the inverse square law. Because if I put my hand over here, you get a little bit of attraction. But as I move my hand closer and closer, that attractive force becomes stronger. So it's like, I don't know what the force is, and it's invisible. It isn't like, ooh, I can see that. Okay? Whatever this force is, I can't see it. Just like gravity. Okay? If I drop this stopwatch, we observe the effects of gravity, but we can't see what's actually happening. So for a while, the electromagnetic force and gravity were actually viewed as being magic. Okay? So it's like, seriously, there was a time in history, if I did this, I would have been burned at the stake. He's a witch! Hey, look! Oh, he's a witch! Okay? Really not. More of a warlock, but anyway. So, because they said, oh, okay, it's magic. Because I'm making the balloon move without an observable force. So, if I put my hand here, and then all of a sudden, that stopwatch began to lift up towards my hand, you would all go, oh, it's magic. It's cool. He's a Jedi. Okay, whatever you want to call me, right? He's a Jedi. Because I can make objects move without any direct observable contact. But if I do this, and I let go of it, how does it work? Oh, that's gravity. So, if I make the watch move up, I get burned at the stake, because that's magic. But if I drop the watch, and it falls, oh, that's just gravity. But then, hold on, whoa. How is it? It's magic if it goes in one direction, but it's gravity if it goes in the opposite direction. It doesn't make any sense. Okay, so that's why for a while they thought, oh, gravity is magic. Because things are moving, and there's no observable force that's making them move. So, when I do this, okay, and it's still there, okay? So, basically what happens is this. This is a story of different breeds of dogs on an atomic level. So, if you've ever been around Chihuahuas, which God bless you if you have. So, Chihuahuas are these yippy little dogs. Okay, right? Worthless little dogs, but they're cute. Some people really like them. I can't stand them. Anyway, so the electrons are like the Chihuahuas of the atomic world. Okay, so they run around. They go yip 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 yip. Okay, and they're very hyper and they move around really quickly. Okay, and they occupy a lot of space. Okay, and they occupy space because they're moving really really fast. Now, the protons and the neutrons are like the St. Bernards of the atomic world. They're just laid there. It's like St. Bernard's sheepdogs, whatever you want. Okay, they're like okay, they're just hanging out. Okay, massive, not going to move around much. Okay, but they create a lot of mass. So imagine the St. Bernards and the sheepdogs are like in the nucleus. Okay, so these big lumpy things in the middle. Okay, and then you have these Chihuahuas running around. Okay, now the St. Bernards are positively charged. They're cool, right? It's like, so they're positive. Chihuahuas negatively charged. Go away. Okay? So what happens is this. My hand is made up of electrons, protons, and neutrons, and it isn't like, oh, that's what makes you a physics teacher, because you have charged particles that make you up. No, everybody is made up of charged particles. And again, conveniently, the universe was created with charged particles. Okay? Because if the universe was just created with neutrons, we wouldn't be here. Because you would never form large molecules. Okay? If the universe is just made up of negatively charged particles, we wouldn't be here. Because if everything was negatively charged, you could never make anything because they'd always be repelling each other. But the same thing is true of positively charged. So conveniently, there's this balance between positively charged particles and negatively charged particles, and they interact, and this is what allows us to have DNA and cells and oxygen molecules and atmosphere. It's kind of cool. So the universe has charged particles. That's an important part. So what happens is that when I bring my hand up to there, what's happened is that the balloon has taken a whole bunch of Chihuahuas from the blanket. So, from the blanket. So the balloon has excess Chihuahuas. Okay? So it's taking Chihuahuas from the blanket, and on the outside of the balloon, there's an excess number of Chihuahuas. Okay? Now, I bring my hand up there. So on an atomic level, my hand is made up of these chunky St. Bernards and sheepdogs that are making up the nucleus. And around them, you have all these Chihuahuas that are running around. Okay, that's cool. And right now, everything is in balance. The Chihuahuas are balancing out the St. Bernards, and the sheepdogs, they're just going, okay, they're just neutron. They're just occupying space and providing mass. And so, when I bring my hand close to them, the Chihuahuas that make up my hand flip out. They go, oh man, there's other Chihuahuas. So Chihuahuas don't like other Chihuahuas. Okay, they don't, because they're the same. They go, man, you're like me, you're annoying. I don't like you. I don't like you either. So they run away. So when I bring my hand up there, the Chihuahuas that make up my hand go, whoop, screw this, we're out of here, because it's like other Chihuahuas. Like, okay, run away. So what happens when I do that is that the St. Bernards and the sheepdogs that make up my hand don't have anywhere to go, because they're just like, stop, don't have anywhere to go. So what happens is that in a very small region, I get an uneven distribution of my Chihuahuas. The Chihuahuas go running away. The St. Bernards are left behind, and they're positively charged. So the St. Bernards, they like the Chihuahuas because they're oppositely charged. The St. Bernards going, hey, little buddy, stop. Okay? Come here, hang out. So when I put my hand up here, because this has excess Chihuahuas, the Chihuahuas that make up my hand go running away. The St. Bernards that remain, which are positively charged, are attracted to the excess Chihuahuas that are on the balloon, and I begin to make it move. Okay? Now, over a period of time, what's going to happen is that the Chihuahuas are going to evenly distribute, because the Chihuahuas don't even like each other. Okay? They don't even like the other Chihuahuas. So right now, Mother Nature's going, yeah, there's a whole bunch of Chihuahuas. I come back hour after this lecture, and I'll put my hand up there, nothing's going to happen, because the Chihuahuas are going to disperse throughout. But right now, there's a whole bunch of excess Chihuahuas on there. I bring my hand there. The Chihuahuas in my hand go running away. The St. Bernards are still left behind. Boom, I get this attractive force. But the cool thing about my hand is that my hand, as soon as I move this away, my hand conveniently doesn't remain negatively charged. So the Chihuahuas, once I move them away from the other Chihuahuas, then they come back to their normal location and go, okay, hey, we're back, it's cool, right? Okay, I scared away the other Chihuahuas, it's cool, right? But as soon as I do this, whoop, the Chihuahuas run away, boom, it's trapped. Now, if I take a second balloon, I'll do this rub here, okay? Now, if I take this balloon, move it near it, okay? What you'll see is that this one also has excess Chihuahuas. So now, everything is overloaded with Chihuahuas. And the Chihuahuas really don't like each other. So what I can do is, I can exert a force over a distance without any direct contact. So I can push that balloon away without ever actually touching it. So there are certain things that we call force over a distance. Gravity is the classic example of that. Okay? When I drop something, there's no direct contact between that object and the earth. Okay? Now, most of the time, like if I want to lift this up, oh, I have to grab a hold of it. I've got to push it. I've got to pull it. I have to physically make contact with it. So the electrostatic and gravity forces, though, those exert forces without a direct contact. So if I do this enough, okay, come on, go, going, come on, okay, all right, go back up. Okay, so it's gravity defying at this point. So what's happened, again, the ceiling is made up of Chihuahuas and St. Bernards, and lumpy sheepdogs. So right now what's happened is that there's enough force between the Chihuahuas, they're negatively charged, and the ceiling tiles to overcome the force of gravity. Sort of says, oh, gravity is really, really strong. Okay? It is. But relative to the other forces, gravity is actually the weakest force. Because I know that that's stronger than gravity, because if gravity was stronger, the balloon would fall. So that electrostatic attraction between those charged particles is stronger than the gravitational force that's pulling that down. Okay, so Evelyn, shut that camera off for a second. Let's go to the back and we'll show you some different. Okay, so this is a way to detect an electric field. So I've got one end, okay? If I touch the other end, it makes noise. So what that shows is that my body is conducting this electric current. Now, I'm going to hold this. You hold that end. Okay? Now touch my hand. Okay? So now that goes all the way around. So now, let's make one big circle and hold hands. This is a kumbaya thing. Okay?
Sorry.
Best friend.
Okay, go on. We're gonna make one big electric field. Okay? Now, so Devin, let go. Now touch. Hold it. Okay, now let go. Grab again. Let go. Okay? So here's the cool thing. As soon as you let go, on the other side of that circle, that stopped. That breaks the circuit, right? We're not making a circuit anymore. So this electric field is being transmitted through all of us. And as soon as, do that again, and if you just barely touch Alexa's hand, just kind of do like tap, tap, okay? Now let go. Okay? So the cool thing about this is that electric field is being transmitted through all of us. And we're making one big circuit. So electric field, that current, is flowing through all of us. So all of those Chihuahuas are flowing through all of us and making one big conductive circuit. Okay, so one of the things, if you want to make kind of on steroids, is this is called a Van de Graaff generator. I'm going to put some little bits of paper up here on top of it. And I'm going to put this on. Here. So this is like rubbing a balloon but on steroids. Okay? So I turn this on. Okay? So what happens is that is generating excess Chihuahuas. And so those bits of paper were gaining that charge. And as it gained that charge, you'll notice the first thing that it did is it began to they stood up on edge. They stood up on edge because of the fact that the Chihuahuas were trying to get as far away from each other as they possibly can. So, okay, still had excess Chihuahuas. And so those bits of paper stood up because the Chihuahuas were trying to get as far away from each other as they possibly could. And when they did that, they stood up because the ends had the Chihuahuas and the bases of these little bits of paper had the excess St. Bernards and sheepdogs. Chihuahuas trying to get away. Now eventually what happened is that we put so many Chihuahuas on there, they said, okay, we can handle this, and we're out. And then they began to defy gravity. So the other thing that you can do to observe the effects of this, and this is what's called a electroscope, okay? Turn this on. And what you'll see, is that when I bring this close, what you'll see is that those leaves begin to move away from each other. So what's happening is that even when I bring this close, those leaves spread out. Okay? So even throughout that space, that electric field is being transmitted through here to this bulb. That is sensing the buildup of the Chihuahuas. The Chihuahuas go, hey, we need to get as far away from each other. So the Chihuahuas all run down to the bottom of the leaves. Once they get there, come on, okay? Once they get there, then the Chihuahuas go, oh, Those Chihuahuas over there, those Chihuahuas over here. We don't like each other. The Chihuahuas spread apart. So I can do the same thing with this balloon. Okay? So I charge that. And then if I bring this balloon close, what you'll see is that those leaves, the leaves begin to move away from each other, like that, because the Chihuahuas are sensing that those other Chihuahuas, and they don't like each other, they're flying apart. Now, if you really want to make a lot of electrons, say, we use this. So this is called a Tesla coil, and turn this on, and so this is making an extreme electric field on the end of that point. Okay? It's very, very concentrated. So we are generating millions upon millions upon millions of Chihuahuas on the end of this. So can one of you reach back to those light switches right there beside that cart and turn that off? Yeah. Now just push the bottom of it, the bottom side. There you go. And do the other one. Okay. So with this one, I'm going to hold this. I'm going to bring this up to the Tesla coil. And what you'll see is that begins to generate electricity. So what's happening is that this is generating an extremely large number of high energetic Chihuahuas. And those Chihuahuas are looking for a place to go. And so the Chihuahuas take the path of least resistance. So the path of least resistance is to flow to this point, and then it flows through the fluorescent tube, and then it hits my hand. And so the reason that this part here doesn't light up is because those Chihuahuas hit my hand. My hand then provides a path of least resistance. So the Chihuahuas flow over my body and down onto the earth. So as I'm generating these, the Chihuahuas coming out like this, flowing along, and in the process, it's exciting the electrons that make up here. So in here, there's a bunch of Chihuahuas, okay? And these Chihuahuas, when they get excited, they emit light, because they're going, wow, this is cool, right? Look, we have excess energy. And when we do that, that's what allows us to have light, because the Chihuahuas that make up this tube are going, wow, this is cool! Okay? They're so excited that they come back down. When they come back down, they emit little photons of light, and that's what allows us to see this. Now, in the extreme case of what you can do, it's a similar type idea. So, here, this. So, I'm going to rub yonder balloon. Oh, a whole bunch of Chihuahuas on it. And then I can actually make the can roll by using the balloon without actually touching it. So what's happening is that the Chihuahuas here, got a lot of them, that come up to the aluminum can. And the Chihuahuas in the aluminum can go, whoop, we're out. So you create a very small region that has a deficiency of Chihuahuas. St. Bernards and the sheepdogs are still there. They become attracted to it. So what happens is I make that roll, okay, because I'm continuously changing the location of that attractive force. And it's creating what we call torque. We'll talk about torque later. So torque is what you need to make something spin. So by taking that negatively charged balloon and bringing it like this, I'm able to make that spin. So if you ever happen to, if you're in desperate need of $5, okay, and you happen to have a balloon and a blanket, kind of prerequisite things, bet someone $5, hello, that you can make a can roll using a balloon without actually touching it. Now, just make sure they haven't been through my physics classes, because they won't take the bet. But if they haven't been through my physics class, you can bet someone $5. I'll bet you $5 right now I can make a can roll using a balloon and a blanket. No, no, you can't. It's like, sure you can. Just do this. Boom. As I say that, come on, roll. Oh, I lost my electron. Hold on. Come on. Roll. I would have lost 5 points. Okay, you got the idea. Okay, now let's say you've made a mess. You have bits of paper all over. So if I take this and move this over to those little bits of paper that I just put down, you'll notice that they stick, okay? And they stick, and you'll notice, especially those ones up there at the top, okay? They're sticking up. Because what's happened is that, again, this boils down to the movement of Chihuahuas. So this has excess Chihuahuas. So if you look at that, those little bits of paper that are touching the balloon are positively charged. The opposite side of those bits of paper are negatively charged. And that's what allows them to stick. Got it? Good? Grand? Back we go. Ready? Okay. So like I said, here is, no, this isn't, but this is a physics book from 1902, okay? So 120 years ago. And if you look in the index in the back, and you try and find the word, like let's say, for example, electron. There's no mention of the word electron. Now, what you do find is you find like elasticity, electric belt, electrical attraction, electrification, okay, electrodes, electrolysis, so electromagnets. So they knew about electricity, okay, and they knew this law F equals Q1, Q2 over D squared. They knew the gravitational force. So in the early 1900s, the physics world, science world in general, was kind of depressed because they thought they had everything figured out. They said, we know the electrostatic force, we can calculate that. They knew the gravitational laws because of Newton. At that point, they could predict like where Mars was going to be. They could predict the lunar phases. They could predict when a solar eclipse was going to be. They thought they had everything figured out. And so the scientific community at that point was basically, they thought they were out of a job because they're saying, there's nothing left to figure out. We understand gravity. We have that equation. We understand electricity. We have F equals K, Q1, Q2 over D squared. We get electricity, okay? We get that. We're done. And literally, they thought the only thing they had left to do was tweak some constants. Everything was done. They had nothing left to discover. Well, here's the problem. Along comes a man by the name of J.J. Thomson. Does anybody remember what J.J. Thomson did from your Chem 1 days? Anybody remember what he did? Oh, Mr. Schwartz is going to yell at all of you. Okay? J.J. Thomson discovered the electron. Okay? Technically, he discovered the charge to mass ratio on these subatomic particles called electrons. And this is in the late 19 teens, okay, around 1918. And so this created a problem because at the time, they had John Dalton's atomic theory. So if you could hearken back to where we were at that point, Dalton's atomic theory said that the universe is made up of these tiny, 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 tiny bits of matter called atoms. So if you go further back to figure out where the word atom came from, The word atom came from the Greeks, and they were called atomists. And so if you translate the word atom from ancient Greek, it means indivisible. Not invisible, but it means indivisible. So here's how the Greeks viewed atoms, okay? And it makes sense. So the Greeks said, all right, let's say that we have a piece of aluminum foil like this, okay? I take this aluminum foil and I tear it in half. Okay, great, still aluminum foil. If I tear that in half, still aluminum foil. Tear that in half, still aluminum. I keep going, and I keep going, I keep going, I keep going, smaller and smaller and smaller, okay? And at some point, if I could tear that so small a piece that if I tear it anymore, it's no longer aluminum. So in the Greek mind, these were like little spheres, almost like Lego blocks. And if you assemble them in one way, you get aluminum foil. If you put them another way, you get an old physics book. If you put them another way, you get penguins, okay? And basically, the world, according to the Greeks, is viewed as Lego blocks. They called them atoms. They said, okay, if you get to that point where I tear this aluminum foil small enough, small enough, small enough, and I can no longer divide it, that last little bit of aluminum foil that I can no longer divide, that's what they called an atom. So John Dalton, in the 1800s, who came up with the first real atomic theory, said, and he had some things right, he said atoms combine in whole number ratios. This is why the formula for water is H2O, 2 hydrogens, 1 oxygen. I don't have H3/4O1/8, okay? I don't have an eighth of an oxygen atom. I don't have 3/4 of a hydrogen atom, okay? You look at every chemical formula that you all studied in Chem 1. It's all whole numbers, sugar, C6H12O6, okay? Whatever it is. There's no partial atoms. So that reinforced the idea of the Greek idea of being indivisible. He said, now he has some things wrong. He said that, oh, all atoms of the same element are identical. They had no concept of isotopes because of the fact they didn't know about neutrons at that point. The other thing that he had wrong was that he said they were indivisible. Okay, so because John Dalton went back to the ancient Greek text and he pulled out that word atom, and that's where the word atom came from. And he said, okay, atoms you cannot divide them. So that was the old ancient Greek philosophy. And everybody was cool with that for about 100 years. Everybody is cool with this idea. Okay, atoms can't be divided, boom. And everybody's happy. It worked. So J.J. Thomson comes along and finds the electrons like, oh man, this screwed everything up. Because, okay, there's negatively charged particles. Now at this point everybody goes, well, if there's negatively charged particles, there has to be positively charged particles. Oh, great, okay. What do those look like? Oh, and they knew that atoms were really, really small. Like I said, 94,000 atoms stacked side by side by side equal the thickness of this. So they knew atoms had to be incredibly, incredibly, incredibly small. And then they said not only atoms are incredibly small, now there's stuff that's inside of them that's smaller than the atoms. Like, oh, what do we do now? So the first model they came up with was what's known as the plum pudding model. Okay, now you have to also understand the geographic location where all this was happening. This was happening in England at Cambridge University. And so that's where all the physicists were. Now, here's the odd thing about this story of chemistry, okay, and the structure of the atom, is that you always learn it in a chemistry class. Oh, here's the history of the atom, okay, J.J. Thomson, Ernest Rutherford, all these guys. Well, they were all physicists, okay? No chemists were involved in this story. The chemistry department tells the story, but they were all physicists. Now, here's the classic idea of how physicists view the world, okay? So let's say you give a Volkswagen Bug to a physicist, and you say, hey, what's What's the Volkswagen Bug made of? I don't know. Let's find out. So we'll run it into the wall at 10 miles an hour. Okay, look. Little bit of a bumper fell off. That was cool. Okay. 10 miles an hour is cool. What happens if you do 100 miles an hour? Okay, let's get the Volkswagen. Donna, have you crashed a Volkswagen Bug into a wall? Okay, Devin's looking at you like you can relate to this. So then you get it up to 100. Oh, look, okay, there's a fender. That was cool. If 100 is good, 500 must be better. Now we're approaching the speed of sound. Oh, look, glass comes flying off. There was an engine. Okay, cool. Let's take that engine and get it up to like 1,000 miles per hour, and we'll smash the engine into the wall. Cool, okay? Oh, look, there was a piston inside the engine. That's handy. What's the piston made of? I don't know. Let's get two pistons going together in opposite directions at like 10,000 miles per hour, and we'll smash the pistons together, and we'll see what the pistons are made of. And that's how physicists viewed the world. Physicists like to smash things together and see what goes flying off. And so we still have that mentality. So if you study like particle accelerators work by basically, we're going to get subatomic particles, we're going to smash these things together at almost the speed of light and see what goes flying off of them. Okay, that's still the same mentality. So the physics department takes over this job of saying, okay, well, what are particles made of? They didn't have anything else to do because they had figured out gravity. So it's like, okay, well, let's figure out what the universe is made of. So Thomson comes along, he finds the electron. Cool. Okay, nice. So they said, all right, how do we explain this? Because no matter what model that you have to explain the universe, one of the key components that you have to explain are two things. Atoms are fundamentally neutral, okay? So when I put my hand here, I don't have to worry about my hand like pushing the desk away because they're the same charge, or I put my hand here and they're oppositely charged and they begin to move towards each other. Under normal circumstances, things are neutral, okay? The other thing that you have to explain is the stability of atoms, okay? And atoms are very stable, and that's a good thing, okay? I've been teaching behind this desk since the fall of 1994. Okay, literally, that's how long I've had this particular desk. It's the fall of 1994. Much longer than you all have even thought about being on this earth. Okay, fall of 1994, I've had this desk. So when I walk in the morning, there's a whole bunch of things that I worry about. Okay, what's going to happen? The kids are going to be gone. What's the weather going to be like? One of the things I don't worry about is if me looking at this table, and all of a sudden, like my table is gone and it's changed into like a squirrel. Okay, it's like, what happened to the table? I don't know, it's a squirrel. And so there's like this rabid squirrel running around my room, and my table is gone. Okay, I don't even have to worry about like happening to the edge. This edge has been here for a long time. Okay, it's stable. So whatever the model is, it had to explain why atoms are stable and why they are neutral. So the first model they came up with, and again, this is a British influence, okay? They came up with what's called, we'll call it the plum pudding model, okay? Say the plum pudding, imagine like this dough of atoms, and within that they have these negatively charged raisins, okay? And it was kind of cool. And they said, okay. So they kind of kept the Lego theme, and they said, okay, we'll have some negatively charged, and we'll have some positively charged, and it's stable. Because you're going to balance out the repulsive nature of the like charges with the attraction of the opposite charges. Everything is in balance, okay? And that worked. It was cool. Explained the stability and explained why atoms were neutral. Yin and yang, positive and negative, attraction, repulsion. It's balanced. Then the physics department got involved. So if you remember back to your Chem 1 days, there was a guy by the name of Ernest Rutherford. So Ernest Rutherford did what was known as the gold foil experiment. So he took gold foil, so instead of aluminum foil, he used gold foil. And the beauty of gold foil is that gold has a very, very unique ability because you can make it into extremely, extremely thin layers, okay? Like basically 1 atom thick. So Ernest Rutherford was a physicist. Keep this in mind, he was a physicist. So he had this sheet of gold foil, and he used a radioactive source called thorium. And he put this thorium in a box. And this thorium would go through radioactive decay. And it would kick out these particles, okay? Now, everybody has this idea, like you could see these particles like they were little BBs that were shot out. They were called alpha particles because they didn't know what they were. But what it turned out is that they were a helium nucleus, okay? And if you remember, harken back to your Chem 1 days. So this is the mass number, has 2 protons and 2 neutrons. This is the atomic number, 2 protons. And this indicates that it has lost 2 electrons. So this is basically nothing but the helium nucleus, okay? That's all it is. Didn't know what they were, called it an alpha particle. Didn't know what they were, called alpha particle. And so what he figured out is that these particles were being shot out from this radioactive source. And the only way you could see them is if you had a phosphorescent screen and a darkened room. And every time one of these particles would hit that screen, you would see a flash of light. So you couldn't see the actual particles. All you could see was this flash of light when the particles would hit. And what he figured out is that he knew that these particles were positively charged because he used like a positive and negative terminal on a battery. And he figured out that the particles would go away from the positive and towards the negative. So he knew these things were positively charged. So he shot these particles at this sheet of gold foil. These particles are going towards this thing. Okay, it looks solid. You couldn't see through it. And over here, there was this screen. Okay, and what he figured out as these particles went through and hit that screen, almost all of them went straight through. Okay, literally, almost all of them went straight through. So what that told him was that this material, whatever it was mostly empty space. So we will finish this discussion tomorrow. I know you don't have